So here I'm going to discuss additional note 1, where the explanation was given how canonical transformation is related to a particular canonical transformation is related to time evolution, and how action is involved in that discussion. The technical details of this discussion can be found in the lecture. The goal of this discussion is to clarify its relevance more intuitively, and the procedure also more intuitively, so that we have a better perspective of what is going on. So let me begin by explaining why it is important. We have the standard formulation of quantum mechanics, which is given by the Hamiltonian. Hamiltonian, that is, we also refer to as Schrodinger description, but we argued that this is not very suitable for generalizing to a relativistic description, because time here appears very explicitly in asking the question, because Hamiltonian is a generator of time evolution. So this has a relation with time evolution, a very particular relation, which is like a generator of a transformation. So time translation is generated by Hamiltonian. It is in that sense time evolution is related to Hamiltonian. It's a very technical point, and we are all familiar with this picture. Now, if you want to go to a relativistic description where time does not appear that explicitly in this sense, then one would wonder that how can we describe a dynamical theory like that, because the main question of a dynamical system is to basically address time, how it evolves in time. So this is where the technical distinction comes. Time evolution is related to Hamiltonian in a particular way, but it is also related to action in another way. Hamiltonian generates time translation as a transformation, and action generates time translation viewed as a canonical transformation. These are very technical statements, and it is the reason why action is more suitable for a relativistic theory is this one, which is a very technical point. So this is not very standard. We don't discuss it too many times in the physics that we have discussed earlier. So this is why it deserves an attention, and we need to explain. So that is the motivation. Now, in this technical slide, I have explained what canonical transformation is, etc. So basically, we have one pair of phase space variable, and we go to another pair of phase space variable, which are equally good in describing dynamical system, in the sense that both the sets satisfy fundamental Poisson bracket relations, and the equations of motion take the same form. Okay. So now what this discusses is that there is a canonical, so any transformation that relates this type of variables, both of which satisfy Poisson brackets, is called canonical transformation. And there are various types of canonical transformations, and that has been explained here, which is related to the Hamilton's principle. Now, then action, which basically answers the question of how to address questions related to time evolution, but not in a Hamiltonian sense, but in another sense, which is more suitable for relativistic description, is the relevance of that action is coming through a specific canonical transformation. It's not that any canonical transformation is relevant in this discussion, a very specific canonical transformation, such that the generator of that canonical transformation is of this form. It depends on x, x prime, and t, and such that the equation of motion for the new variables are given by these equations. Okay, so both x prime dot and t prime dot are 0, and as a result, so this relation is true. Both these relations are true for any time, which means that x prime and t prime do not depend on time at all. So they are given by certain numerical constant. So that is the description. And this Hamiltonian formulation, Hamiltonian is algebraic in x and t. Therefore, when you write Hamiltonian in terms of these dynamical variables, that is also just a numerical factor, just a numerical constant, because x prime and p prime both are numerical constants. So you can choose Hamiltonian can be shifted by a constant. All these analysis will still remain the same. If you can choose that shift in a particular way, so that h prime is 0. Now, this structure, when you come to this structure, nothing about the system has remained anymore, because it has too little information about the dynamical system. And it turns out that from any dynamical system xp you start, you can always come here. And that's a result of the fact that Hamiltonian is conserved. It's time independent. So if Hamiltonian is conserved, then you can always go to a system where, so in a usual system xph, you have to find the solution for x and p, plug them into the form of Hamiltonian. Hamiltonian is given in terms of the phase space variable x and p. And when you calculate the solutions for x and p, you plug them back into the Hamiltonian, and then discover that it does not depend on time. Though both x and p individually are dependent on time, when you plug them into the expression for Hamiltonian, then it becomes time independent. It gives you a constant, right? Now, so that means this is not in the dynamical problem itself, it is not manifest. You wouldn't know a priori that it's a constant or it's time independent. In this variable that is made manifest, this is something that is true whatsoever. So the question is that could you go to could you go to a phase space system where this is manifest and this is that system? But you make that manifest, but at the price that you pay is that almost all the details of the dynamics is erased, because there is nothing left. Nothing is time dependent here. That is a disadvantage. And any system can be brought to this thing, this type of a system. So once you are convinced that you can choose such a system, the question is that how to find the transformation. There must be a transformation relating these two. And you do a technical analysis and find that transformation, which means find the relation between x, write x in terms of x prime, p prime, and t. So if you look at this expression, then it's clear that x prime, p prime are just two constants. Then it is clear that this must be the solution of the original problem, because in the original problem we know that this structure is supposed to give you the solution x as a function of time and also the initial conditions. So there will be two arbitrary constants. This system x prime dot and p prime dot being 0, they imply that both x prime and p prime are two arbitrary constants. So that exactly this is the form that this equation takes. So this is the advantage of this system, because the system erases all the non-trivial facts about the dynamics. All the non-trivial facts about the dynamics is now encapsulated in the canonical transformation itself. So it means nothing to say that this exists. It means nothing about it tells nothing about the system. Given any system, when the non-trivial thing that you achieve by going to this system is to find this transformation. Okay, so finding the transformation here, finding the canonical transformation is equivalent to solving this system as x as a function of t and the initial conditions. So this is one way of solving the system. Just take the equation of motion, solve it, and find x as a function of the initial conditions and time. The other way is to find the canonical transformation, this system which apparently looks trivial. Okay, so all the non-triviality of the dynamics is hidden in this transformation itself. Okay, now this transformation is generated by S, and then there is a bit of technicality how that is related to the action that is used in path integral, that will be used eventually in path integral, which is this equation, and the solution is given by this. From here you can argue that ds dt is given by this, and then if you solve it, then you get this equation where the time that action has, this is x prime and t, this time is actually the upper limit of the time integral in the usual action. This is the usual form of the action. Okay, and this is the generating function. How is this generating function is related to the actual action that we talk about? So this is the actual action that we talk about, and see the explicit time dependence in that generating function is the upper limit of the time integral in the actual action. Okay, now what about the other variables on the two sides? We have to match all the variables that are appearing on the two sides and find relation between them in order to understand this relation. So let's have a look at that. In order to calculate the right-hand side, you need to know the paths of both x and p paths. So x and p paths will be given by boundary conditions. So this is your initial time ti, final time is t, and then the initial condition at ti is say x0, and the final thing is say x. Similarly, for p, we have p and p0 for the p path. So these are the four things that we need. So on the right hand side we have t, ti, x0, and p0. Right. On the left hand side we have x prime, of course we have t, and there is some relations, x as a function of x prime p prime t, and p as a function of x prime p prime and t. So this p, if you go to the theory of canonical transformation, p is given by del s del x. So once you know s as a function of x, that already gives you p as a function of x prime and t. So let's look at the relations that we have between the two sets. One is on the right hand side, as I said, t, ti, x, p, and x0, p0. These are the final configurations. These are the initial configurations, x0, p0. And on the other side, we have t, we have x prime and p prime, and then the relation x prime, x as a function of x prime p prime t, p as a function of x prime p prime and t. Now let's relate them. So T is there, that is matching. So X0 and P0 are the same relations with T equals Ti. Okay. And so basically, X prime, P prime are traded with X0, P0. And XP, X prime, P prime are traded with X0, P0 through this relation with T equals Ti. And XP is related to this XP with T equals T, with time equals T. So this is how knowing this set of quantities is equivalent to knowing this set of quantity and vice versa. That is how the relation is working out. Okay. Now let me point out one particular difficulty in my description which appears here, which is this T dependence, explicit T dependence in the Hamiltonian. Now whatever I just described here, for that you just erase this or ignore this T dependence. If you do that, then Hamiltonian is basically a constant, time-independent constant, in which case H prime is also a time-independent constant, and therefore you can give a constant shift to make it 0. Okay. Now, then everything will go through whatever I just said. Once that argument is understood, that can be generalized to a Hamiltonian with an explicit time dependence. This time dependence has nothing to do with the time dependence of S, the generating functional. Even if this is time independent, there is no explicit time dependence, this relation holds, which says that S has an explicit time dependence. Okay. So once you understand the argument for a system where a Hamiltonian does not have explicit time dependence, then you can convince yourself that everything goes through if you just extend it to a situation where Hamiltonian has explicit time dependence. And then it will also induce through this relation an explicit time dependence in H prime. Okay. That's the only thing. So this only one T that appears here is a bit confusing, but you can understand this way. I mean, for this purpose, for the point that I'm trying to make in this part of the lecture, this explicit time dependence was not needed. So it is, but this is right nonetheless. You can do it for when you can extend the argument in that situation as well. So that is one clarifying remark. Okay.